There is a moment in human history when everything changes. A moment when a technology is no longer just a tool, but a force that reshapes the world. That happened in England when the first steam engine powered a factory. It happened in Detroit when the assembly line turned the car from a luxury item into a mass-produced product. And it happened in the 1990s when the internet stopped being a military project and started to redefine society. Every time, the people who were in the middle of it thought they were just building a new machine, but in reality, they were building a whole new world. And that's exactly what's happening again right now. Only this time, not in a factory in Manchester or in an assembly hall in Michigan, but simultaneously in an X-ray facility. A rocket launch site in Texas, a research lab in Boston, a moon mission in Florida, and a server room in Palo Alto. The third industrial revolution was digitalization. What comes next doesn't have a proper name yet, but it has a direction. My name is Servan, and this is Mars Chronican. To understand where this journey leads, we have to start with a concept so radical that most people instinctively reject it. Not because it's wrong, but because it's taken to its logical conclusion. It comes from a Hungarian-American mathematician who worked on the foundations of modern computers in the 1940s. His name was John von Neumann, and his idea was simple, but with a consequence that still hasn't been fully understood today. Von Neumann imagined a machine capable of reproducing itself. A machine that takes raw materials from its environment, builds an exact copy of itself from them, and then that copy does the same thing. And the copy of the copy, and so on. On Earth, it sounds like a nightmare from a science fiction movie. But von Neumann wasn't thinking about Earth, he was thinking about the universe. Imagine sending just one such machine into space. It lands on an asteroid, a moon, or another planet. It starts mining resources. It builds a copy of itself. Both machines build more copies. After a few generations, there are hundreds. After a few more, thousands. Each individual machine explores, builds, and sends data back. On cosmic timescales, a single von Neumann probe could map the entire galaxy. That's not fantasy, it's mathematics. Let's put aside the feasibility for now. And a few months ago, Elon Musk tweeted exactly this term out into the world. In the context of Optimus, Tesla's humanoid robot, and the question of what autonomous, self-replicating systems can accomplish in space. It was a short post, but it has a very long history. But before we look into the future, we need to briefly look back. This isn't the first time we've been here. The first industrial revolution began in the second half of the 18th century in England. Steam power replaced muscle power. Factories replaced craft workshops. Cities boomed. The world population began to grow because food could suddenly be produced in quantities that were previously unimaginable. In less than 100 years, the way people lived and worked had completely changed. The second industrial revolution at the end of the 19th century brought electricity, steel, and the assembly line. Henry Ford didn't invent the car, but he made it mass-producible. The Model T wasn't the fastest or most elegant vehicle of its time, but it was the first that an ordinary worker could afford. Standardization and mass production reordered the world for a second time. The third industrial revolution, that is digitalization, has turned information into a resource. Knowledge that was once stored in libraries and required days of research could now be accessed in seconds. Production processes were automated. The global economy became interconnected in a way that had previously been structurally impossible. Each of these revolutions had something in common. They didn't just accelerate existing processes, but they changed the fundamental logic by which resources, labor, and knowledge are organized. And that's exactly what's ahead of us again now, only with one crucial difference. The first three revolutions took place on Earth. The fourth begins here, but it doesn't end here. To understand this, we need to consider everything happening simultaneously right now. We're talking about three developments that emerged independently of each other, and now they're starting to reinforce each other. The first is the development of autonomous humanoid robots. The second is the ability to process raw materials off Earth, directly on site and without transporting them back to Earth. The third is the concept of self-replicating systems, that is, for Neumann logic applied to real hardware. None of these three elements alone is a revolution. But together they describe something that has no precedent in human history. Let's start with what is most tangible. In 2021, Tesla began to seriously consider developing a humanoid robot. As a very concrete product goal, Optimus, as it's called, is already being used in Tesla's own factories today. Not in large numbers, not perfect, not independent, but it works. It sorts components, performs simple assembly tasks, and navigates through a factory hall that wasn't built for robots, but for humans. They still need supervision, but they learn quickly. That's the crucial point. Previous industrial robots have been extremely powerful, but only in a single precisely defined task in a precisely defined environment. A welding robot in a car factory can perform thousands of welds per day, faster and more precise than any human. But if you move it just 3 meters to the left, it's practically useless. Humanoid robots approach the problem differently. Instead of adapting the machine to a task, you build a machine that can adapt to any task. A machine that works in a world built for the human body. With door handles, stairs, uneven floors, and tools that require hands, the advantage is conceptually enormous. The disadvantage has always remained the same. This flexibility requires an enormous amount of computing power, energy, and coordination. A human body is the result of millions of years of evolution. Replicating it was simply too complex. The machine uses mechanics and artificial intelligence, large language models, reinforcement learning, and multimodal perception systems. These technologies have made progress in the last 3 years that has fundamentally shifted the field, and they're not just relevant for Optimus. They are relevant for any robot that is supposed to act autonomously in an unstructured environment. Tesla is not alone. Boston Dynamics, known for the four-legged robot Spot and the humanoid Atlas, has demonstrated in recent years what mechanical precision and movement intelligence can achieve. Atlas can walk, jump, and do somersaults. With a fluidity of movement that seems almost uncanny at first glance. But Boston Dynamics has a different profile than Tesla. Their focus has long been on mechanical performance and less on industrial scalability. That's changing now, since the company has been pushing more towards commercial applications under Hyundai's ownership. Then there's Figure, an American startup that's working with BMW and is already using its Figure O2 robot in production. Agility Robotics with Digit specializes in warehouse logistics. And then, and this is a point that is systematically underestimated in Western media, there's China. Unitree, a Chinese manufacturer, produces humanoid and quadrupedal robots at a fraction of the cost of Western competitors. And their level of maturity is astonishing. The H1 and G1 from Unitree are not only impressive technical achievements, they are affordable. The G1 costs under $20,000. For comparison, a similar robot costs several times more. By the way, Musk also says that Optimus is supposed to cost under $30,000. Although that probably won't be achieved at the start of sales, that's the same pattern we know from the solar industry and from battery production. China is scaling up while the West is still discussing concepts. But all of this, Optimus, Atlas, Unitree, is still happening on Earth, in factories, warehouses, and offices. What happens when we bring these machines into an environment where there is no human infrastructure? In an environment where there is no breathable air, no roads, no supply chains, no workshops. So on the moon, Mars, or in the asteroid belt. And this is exactly where the conversation about von Neumann probes stops being a philosophical consideration and starts becoming an engineering question. To answer this question, we need to understand what the fundamental problem of space travel has been so far. It's not the rocket, it's not the physics, it's not even the money, although of course that also plays a role. Everything humans need in space, every screwdriver, every cable, every screw, every drop of fuel, every meal, every liter of water. Until now, everything had to be brought from Earth. Against gravity, using rockets and fuel at a cost that until just a few years ago was several $1,000s per kilogram. That means every space mission is essentially a logistics operation. An extremely expensive, extremely fragile logistics operation where every gram counts and every mistake can potentially be fatal. That has shaped the entire architecture of space travel. Missions are kept small because every kilogram of payload represents a huge cost factor. Infrastructure is kept to a minimum because every structure has to be built on Earth first and then transported into space. And people are kept in space for as short a time as possible because every person in space needs oxygen, water, food, and medical care. All things that have to come from Earth, completely aside from the fact that most people also want to return safely to Earth. But this boundary is beginning to aufzulösen. Der Schlüssel, a concept called in situ resource utilization, or ISRU for short. In plain English, using resources on site. The idea is simple. Instead of bringing everything from Earth, you just use what's already there. On the Moon, there is water in the form of ice in permanently shadowed craters at the poles. This ice can be split into hydrogen and oxygen, both for breathing air and as rocket fuel. The lunar soil itself, the so-called regolith, consists largely of oxygen, silicon, aluminum, iron, and titanium. All of these are materials you can build with. If you like the topic, feel free to give the video a boost. That's really important so it gets shown to more curious people like you and me. And if you haven't done that yet, feel free to subscribe and maybe consider supporting the channel as a member. Our members to see days and sometimes even weeks in advance. Thank you all, and now back to the topic. The problem so far was, how do you get access to these materials? How do you process them, and how do you make something useful out of them without bringing an entire factory from Earth? And this is exactly where Blue Origin enters the stage. In 2024, Blue Origin introduced something that almost went unnoticed by the public. It may be one of the most significant technological demonstrations of recent years. They call it the MRI reactor. MRI stands for Molten Regolith Electrolysis. In German, that's Schmelzflusselektrolyse von Mondgestein. The principle sounds almost unbelievably simple when you hear it for the first time. You take lunar rock, raw, unprocessed regolith, just as it lies on the surface of the moon. You heat it up so much that it melts. And then you pass an electric current through this molten mass. What happens? The oxygen atom separates from the metal oxide compounds in the rock. It rises as a gas, pure oxygen, directly usable as breathing air or as an oxidizer for rocket fuel. What remains is a melt of pure metals: iron, aluminum, titanium, silicon. No chemicals, no water, no complex process steps, only electricity and heat. Blue Origin not only described this process theoretically, they demonstrated it, and the results were clear. The reactor produces oxygen and metals in a single continuous process. What that means becomes clear when you put it into perspective. A lunar colony needs 3 things more than anything else: breathable air, building materials, and fuel. The MRI reactor provides the basis for all 3 from a single raw material that is literally available everywhere on the moon in unlimited quantities. That's a paradigm shift. And nobody is talking about it. But now comes the crucial step. Because an MRI reactor alone is not yet a self-sustaining system, it needs someone or something to operate it. That maintains it, processes the materials produced, builds new structures, and fixes errors. On Earth, those are humans or specialized industrial robots in controlled environments. On the Moon, the problem is more fundamental. Humans are expensive, risky, and biologically limited. Specialized industrial robots only work in environments that have been prepared for them. What you need is a system that's flexible enough to handle an unprepared, chaotic environment, and autonomous enough to operate without constant human supervision. What you need is a humanoid robot. And now, for the first time, the three threads of this story are really starting to come together. Imagine the following scenario, not as science fiction, but as a logical consequence of things that already exist today or will exist in the near future. A spaceship, let's say a Starship or Blue Moon, lands on the Moon. Not with a crew, but with cargo, an MRE reactor, a power supply, and 20 humanoid robots. The robots unload the cargo. Completely autonomous, coordinated, and without instructions for every single step. They set up the reactor, they lay cables, they activate the power supply. The reactor begins to melt lunar rock. Oxygen escapes, metals accumulate. The robots take these metals and begin to build simple structures. Not complex architecture. At first, only frames, supports, and containers. Simple shapes made from simple materials produced directly on site. Over time, these structures become more complex. The robots produce components they need themselves, spare parts, reinforcements, and new tools. The energy supply grows as more solar panels are installed. The reactor runs continuously because it doesn't sleep, doesn't eat, and doesn't need a break. And eventually, that's the von Neumann moment. This system produces enough resources and enough infrastructure to build a second reactor. And a second group of robots. This isn't too wild a speculation, but rather a direct extrapolation from three technologies that are real today. What this means in practice is best understood through a comparison. In the first industrial revolution, a steam engine took over the work of maybe 20 people that was revolutionary. But the steam engine needed coal, which was mined by people. It needed maintenance by people. And it could only perform a single clearly defined task. In the second industrial revolution, the assembly line increased production speed tenfold. But the assembly line needed a factory that had to be built beforehand. It needed engineers to design it and workers to operate it. What we're describing now is something structurally different. A system that supplies itself with resources, that expands on its own. That doesn't require any pre-existing infrastructure because it creates it itself. The previous industrial revolutions have made human labor more efficient. What is emerging now could completely replace human labor in certain environments. And not because we humans are worse, but because humans simply cannot survive there biologically. The Moon has no atmosphere. Mars has one, but it's poisonous to us humans and far too thin to breathe. And that brings us to the question that takes this whole line of thinking to a new level. What happens if this system doesn't stay on the Moon? The asteroid belt between Mars and Jupiter contains resources on a scale that surpasses all economic categories we know today. A single metal-rich asteroid, let's say Psyche 16 to give a concrete example, is estimated to contain iron, nickel, and other metals worth several tens of thousands of quintillions of dollars. A value so absurdly large that it is economically meaningless. Not because the resources are worthless, but because there is no market that could absorb that amount. Not yet? But what if these resources didn't have to be transported to Earth? What if they were used directly in space to build more infrastructure, replicate more systems, and enable more missions? That's the real vision behind von Neumann's concept when applied to space travel. Not a probe that maps the galaxy, but a system that unlocks the resources of the solar system. Autonomous, self-sustaining, and exponentially scalable. A civilization that is no longer limited by the resources of a single planet. But, and this is important now, we shouldn't pretend that we're on the verge of it. There are still enormous technical, logistical, and economic hurdles between what exists today and what I just described. Autonomous robots on the moon operate under conditions that no test lab on Earth can fully simulate. Moon dust is abrasive in a way that destroys machinery in unexpected ways. Temperature differences of over 250 degrees Celsius between day and night cause stress on materials. The MRI reactor was demonstrated in the lab, but that's far from the same as continuous operation for months on the lunar surface. And humanoid robots, even the best ones that exist today, are still far from being truly autonomous in a completely unstructured environment. They are getting better and quickly, but the leap from a controlled factory floor to the lunar surface is no small step. There is a number that puts all of this into a different perspective. Elon Musk has mentioned it several times in different contexts and with different wording. But the core is always the same. To establish a self-sustaining civilization on Mars, you need about 1 million people up there. 1 million? That sounds absurd. Today, in total, fewer than 700 people have ever been to space. And most of them only for a few weeks. But Musk doesn't mean that as a short-term goal, he means it as a structural necessity. A colony that can feed itself, defend itself, repair and reproduce itself without constantly relying on supplies from Earth needs a critical mass of people, skills, and infrastructure. The problem is, bringing 1 million people to Mars with conventional space travel, even with a drastically reduced launch price thanks to Starship, would take decades and cost trillions. Unless you don't send 1 million people, you send the machines first. So what would be the minimal initial equipment you would need to send to Mars so that the system could scale up independently from there? No one can answer that with certainty today. But you can clearly name the 4 building blocks. First of all, you need an energy source. Solar energy works less efficiently on Mars than on Earth, but it's sufficient. Nuclear power would be better because it's independent of dust and weather. NASA has already developed a compact reactor called kilopower, which was designed specifically for this purpose. You need to process raw materials. Mars has iron, silicon, aluminum, magnesium all in the soil. An MRI-like process adapted to Martian soil could extract these materials. Next, you need manufacturing capacity. Simple additive manufacturing, that is 3D printing with metal powder or regolith-based materials, is already at a level today where it can produce not only simple structures and spare parts, but also highly complex machines like the Raptor engine from SpaceX. And they are far from the only ones using this manufacturing method. I made the Raptor engine myself here in the studio with the core one from Prusa. Of course, I'll link the model for you below, and you'll also find my affiliate link there. My printer only works with plastic filaments and not metal powder, but it's just as impressive. Today we'll keep the ads short, so let's get back to the topic. Last but not least, you need systems that coordinate, maintain, and operate all of this autonomously without waiting for a person who, in the best case, is 40 minutes away because of the signal delay. When these 4 elements come together and run reliably, something is created that has never existed before in the history of space travel. An extraterrestrial production base that sustains itself. And now we're going to scale this up further. Because that's the real question. Not whether it's possible, but what happens if it works. A self-replicating production base on Mars grows exponentially as long as energy and raw materials are available. Both are available on Mars in practically unlimited quantities. Solar energy is available as long as the sun is shining. Raw materials are literally everywhere on the surface. That means growth is not limited by external factors. It is limited by the internal logic of the system, by the speed at which machines can build new machines. In the early phase, that's slow. Maybe the first system produces enough material in a year for a second unit. In the second year, there are 4, in the third, 8, and in the 10th year, if the growth rate remains stable, there are over 1,000 units. Although you can't really assume that everything will work smoothly right from the start, All operations will start slowly and only accelerate over time. That's the mathematics of exponential reproduction. The same mathematics that describes biological growth. The same mathematics behind Moore's law. And the same mathematics that John von Neumann applied to space in the 1940s. The difference from biological growth. Apart from material fatigue, there are no diseases and no food shortages. The system keeps growing until it reaches an external limit. And on Mars, this limit is astronomically far away. But let's pause for a moment on a question that is often skipped in this discussion. Who controls all of this? A self-replicating autonomous infrastructure on another planet is no longer a tool in the classical sense. A tool does what you tell it to do. A von Neumann machine does what it was programmed to do, even when no one is watching anymore. That is a fundamental governance question. If SpaceX and Blue Origin are the first to place these systems on Mars, who do they belong to? Who owns the infrastructure they build? Do Irish property rights apply on a planet where there is no international or interplanetary legal system? The Outer Space Treaty of 1967 says that no state can claim celestial bodies. But it says little about what happens if a private company builds a self-sustaining infrastructure there that in fact can no longer be removed. These aren't questions that engineers answer, but they are questions that need to be answered before the engineers are finished. Back to technology. Because there's another aspect that has been neglected so far. Communication and autonomy are two sides of the same challenge. A robot on the moon can theoretically still be remotely controlled from Earth. The signal travel time is only about 1.3 seconds each way. Impractical, but doable. A robot on Mars, on the other hand, is between 3 and 24 minutes away from Earth, depending on the positions of the two planets in their orbits. Remote control in real time is therefore impossible. That means any system that is supposed to work autonomously on Mars must have real decision-making intelligence. It can't wait for instructions. It has to recognize problems itself, evaluate them itself, and solve them itself. Within the parameters it was given, that's a different level of autonomy than what today's robots are capable of. A welding robot in a factory is autonomous in the sense that it welds without human intervention. But if something goes wrong, it stops and waits. A Mars robot that stops and waits may have to wait months until a human can remotely diagnose the problem and send back a solution. That would be in slow motion. The technologies we're talking about here are not used exclusively in space. Humanoid robots that autonomously build infrastructure on the moon are the same humanoid robots that are used on Earth in warehouses, factories, and construction sites. ISRU processes that turn lunar rock into building materials are offshoots of the same materials science that will revolutionize terrestrial production. And autonomous systems that monitor and perform complex tasks will not stop at the edge of the atmosphere. The first 3 industrial revolutions have changed work. They have made professions disappear and new ones emerge. They have created enormous prosperity, but also enormous disruptions that took decades to stabilize. What is coming now will do so at a fundamentally different pace. Not over generations, but possibly over years. The real question is whether we as a society can think fast enough to create the structures that will cushion this change before it overwhelms us. Because that's the pattern of industrial revolutions. It's not that they were bad, but that they came faster than the institutions that were supposed to regulate them. And that brings us to the end of this story, or rather to the beginning of the next one. Proxima Centauri was the first neighbor. Mars is the first target. Behind both lies the same question that has driven humanity since the first time someone climbed over a mountain peak and looked into the valley on the other side. What's behind it? And for the first time in history, we have the right tools. A self-replicating machine. A technology that turns moon rock into building material, and a humanoid robot that works in a world not built for him. None of these elements alone is the revolution, but together they describe a moment that we might not truly understand for another 20 or 30 years. Just like the people who saw the first steam engine and didn't know they were witnessing a new era in human history, they saw a machine that produced steam. We see robots melting moon rock. What it is that we're actually seeing, we will only know later. My name is Servan, and that was Mars Chronican. Thanks for watching. Peros Pera ad Astra. Large language models, reinforcement learning, and WARNI. Varni system. Agility robotics. Agility robotics with digit. What would be the minimum initial equipment you would need to send to Mars so that the system could sustain a production base that keeps itself running and alive? The same mathematics as biological growth, max von blah blah blah.